This is 3.1 part 4, and it's the last section of 3.1, and it's another LCM question. This time we're given three numbers, 28, 42, and 63. And we're looking for the smallest number that all three of these will divide into. And the method that we're going to use is a factor tree. So we're going to turn 28 into its prime factors, or prime factorization, by going 2 times 14, and 14 is 2 and 7. And then 42 we're going to write as 2 and 21, and 21 is 7 and 3. And 63, obviously 2 is not going to work. Let's go 3 and 21, circle our 3. 21 is 7 and 3. And let's do our prime factorizations over here. The prime factorization of 28, we're going to do it in order. So 2 times 2 times 7. And then again, for the LCM, you want to change this to an exponent. 2 squared times 7. And then the prime factorization of 42 is 2 times 3 times 7. And there's no exponents there. And the prime factorization of 63 is 3 times 3 times 7 is 3 squared times 7. Our LCM then, what's it going to have? Well, we're going to compare from this list, and this list, and this list. Do we have a 2? We do. We have a 2 squared here, and a 2 to the power 1 here. We pick the biggest exponent, 2 squared. Do we have a 3? Yeah, a 3 to the 1, and a 3 squared, so I'm going to pick the 3 squared. Do we have a 5? We do not have 5. Do we have a, well, 7 would be the next one, then we do have a 7. And then we're going to multiply that through. 2 squared is 4, times 9, times 7, which is going to turn into 252. So in this question, our LCM is 252. It's the smallest number that this, and this, and this will all evenly divide into. So our next one is a word problem. And it says 2 ropes are 48 meters long and 32 meters long. So you've got a rope that's 48 long, and then a guy that's a little bit shorter at 32 long. And I need to cut these ropes into equal pieces. So I need to cut this into a few pieces and this into a few pieces. Problem is that they all need to be the same length pieces, and I obviously don't want to have any waste. That's a whole number of meters. What is the greatest possible length of each piece? So how long can I make each piece? That is a greatest common factor, because I'm breaking it into pieces that are the same size. So what am I going to do for greatest common factor? Look back at your notes if you need to. You're going to turn each of these into their own factor tree, and you're going to find the prime factorization. 48 is 2 and 24, which is 2 and 12, which is 2 and 6, which is 2 and 3. 32 is 2 and 16, which is 2 and 8, which is 2 and 4, which is 2 and 2. So what's the prime factorization of 48? It's 2 times 2 times 2 times 2 times 3. What's the prime factorization of 32? 2 times 2 times 2 times 2. For GCF, we're not going to use the exponents. We're just going to leave them as they are, and we're going to find exactly what the two prime factorizations have in common. This is about a 2, 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 and a 2. So my GCF has a 2 times a 2 times a 2 times a 2, which is 16. What does that mean? That means that I'm able to divide these pieces of rope into pieces that are 16 meters long. And if you think about it, 16 goes into 48 3 times. So I would actually be able to divide this guy into 3 pieces of rope. There's 1 piece, here's 2 pieces, here's 3 pieces, and I would be able to divide him into exactly 2 pieces. So I nicely have 5 pieces of rope that are each 16 meters long.